I actually see it as a time machine which travels outside time across this mathematical space of all possible biology and then can just kind of materialize like the TARDIS.
Welcome to Talk Bio to Me, the show where we sit down with the people building the future of biology. I'm your host, Flo Lumsden, founder of Chorus Studios, a podcast production company where we transform complex technologies and breakthrough ideas into human stories that educate, entertain, and inspire. This year, we headed to SynBioBeta, the world's largest conference for synthetic biology. This mini-pod features some of the most fascinating founders.
We make spores that actually eat the insects.
Scientists.
We have carbon-fixing microbes that can essentially eat emissions.
Researchers.
This is going to make DNA into a programmable material that we can use to turn biology into infrastructure.
Investors.
Because it's garbage in, garbage out on AI. And Mother Nature still works in mysterious ways, right?
And AI innovators.
I'm increasingly excited about AI actually making an impact in the lab.
Shaping the future of biotech. From breakthrough therapies to AI that's beginning to design biology, I discovered one of the most exciting technological revolutions of our time. Okay, talk bio to me. Welcome to Talk Bio to Me with Flo. That's me, of Chorus Studios. So excited to have you both here today. Could you help me out and give a brief introduction to each of you individually, your name and what you do?
So my name is Adrian Woolfson. I'm the CEO of Genyro and also the co-founder along with Kaihang.
I'm a Kaihang. I'm a professor at Caltech. Also, I'm a co-founder of the company at Genyro together with Adrian, and also two other of our co-founders who cannot be here today.
How many co-founders are there?
There are 4 altogether.
Okay, cool.
Yeah. The other 2 are Brian He at the Arc Institute at Stanford and Noah Robinson, who's in Kaihang's lab at Caltech.
Yeah.
Very cool. Genyro, how many years has it been here in the world? Or when was it?
I can answer that one. 1.5 years.
Okay,
Yeah.
so it's very new.
Yes.
What was the impetus? What was the spark of innovation that led to its creation?
In a way, this is the pain and suffering I endured for like over probably 20 years, right? Because I'm in the field of synthetic biology, right? And I need to make DNA from scratch sometimes to encode for functions to cure diseases and so on and so forth, right?
Yeah.
So in my earlier work, I have to make a design and make the entirety of the E. coli a bacterial genome to carry out the new functions. And I can design. I made an invention to basically, once you have 100,000 nucleotides, you can use that as building blocks. But it has been tremendously painful, expensive, and slow to build into that 100 kb building construct. So in a way, the pain and suffering I endured through that was the inspiration of the invention of the technology called Sidewinder, which is a foundational piece of the company Genyro.
Sidewinder.
Yeah, and just to be clear, Kaihang, we were both from Cambridge University, same laboratory of molecular biology, but at different times. And Kaihang built the first ever entirely synthetic genome of a bacterium and then recoded it to give it a totally new genetic code, right? And as he said, don't build the genome all in one go. You build it from kind of building blocks, like those prefabricated units when you see those buildings go up over a weekend from the car park. And it was those units that were very hard to make that Kaihang's new technology solved. So when Kaihang and I were collaborating on another project, I'd started another company before this. But when Kaihang told me about this technology, I thought, wow, this is going to change the world. Right. This is going to make DNA into a programmable material that we can use to turn biology into infrastructure and literally build everything out of, biology, grow things.
Yeah.
That is so freaking cool. I come from a sustainability, climate centric background.
Yes. Yeah.
Right.
So when you talk about growing things like infrastructure, buildings and rugs, that's like, I love that.
Yeah.
I have a funny question for you guys. So you were the first to create synthetic biology or DNA.
Right. So we cannot, we are on the shoulders of the giants.
Okay.
Right. So synthetic DNA, that is a brilliant invention.
Okay.
and that's not us.
Okay.
That is made in the 1970s by Professor Cronus.
Okay.
Right, he got Nobel Prize for the work. But there's a catch. These are synthetic DNA invented back then and also made today. They are fairly short, of
Okay.
only a few hundred nucleotides.
Short
And
strands.
short strand of
Very
DNA.
short pieces.
Yeah.
Yeah.
They are kind of like equivalent when you can using the printing press to print a page.
One
right?
page,
One
yeah.
page is each oligo, synthetic oligo, is equivalent to one page. But you need multiple pages to form a book.
Right.
The same way you need multiple synthetic oligos to be pieced together in the right order to form a gene for the sustainability, for the function to cure diseases, so on and so forth.
So what
Yeah.
Kaihang did, so prior to us, you could make very small bits of DNA, and you could actually make a long bit like you did, but it was really, really painful. And there was some, like when Kaihang made the synthetic E. coli, he had to leave out a bit of it because
Yeah.
you just couldn't make it.
Yeah.
And so what Kaihang did is he invented the concept, he brought the concept of page numbers from the publishing industry, from books into DNA,
Yeah.
right? Because it actually took the publishing industry 90 years to discover the concept of page numbers. The first books, the Gutenberg Bible, didn't
To
have
us, it
page
seems
numbers.
so obvious now.
Yeah, it seems obvious.
exactly.
But once you
Yes,
have
that's-
the page
that's
number,
bizarre thing. Yeah.
once you have the
Yeah.
page number concept,
Yeah.
you can actually assemble DNA programmatically
Mhm.
without having to, if you had a book and it fell apart, you'd have to reassemble it by reading the beginning and the end
Yeah.
of each page and kind of matching them up. And that's how all existing DNA is made. The problem with that is if the DNA is very repetitive, you can't match it up because it all looks the same, right? And half of the human genome is like that, and 85% of the plant genome is like that. But with Kaihang's method, like with page numbers, you don't look at the text, you just can programmatically assemble the pages and as many as you like. And the error rate of the method is one in...
maybe you could.
Actually, I remember this from the press release.
Yeah. So with conventional method,
Yeah.
without the equivalent of the page number,
Mhm.
the misconnection rate in which you put the two pages in the wrong order, that is one mistake out of every 10 to 30 connections.
Yeah, so every
It's a lot.
10 to 30
Yeah.
pages, you've got the
It's
wrong
wrong,
page
yeah.
in the book.
So
Yeah.
our misconnection rate is way lower. If I'm gonna ask you to give a number that will impress
I
you,
think she
because you have
knows.
very very high standard.
I already
One out of
know.
a
You already know.
okay.
1 in 10 million.
Yes.
So it's
yes.
basically you can make a book
I
with
was
10
impressed
million
with
Okay,
with
okay.
10 million pages,
Mhm.
and only one page will be in the wrong order
Yeah.
instead of 1 in 30.
Yeah.
And that's
So-
not an incremental
yeah.
change.
So-
That's an exponential change.
Yeah, so in a way, this is from before the invention from 1 in 10 to 1 in 10 million. So
Right.
there are many different criteria you measure the connection, right? But if you just reduce that just to the misconnection rate, then that is literally 1,000,000 times better.
And using this tool, you can build synthetic
DNA.
DNA.
For any functions.
for any function.
Yeah, and there are some low-hanging fruits, and in one of the low-hanging fruits we identify in particular is using the messenger RNA vaccine to fight against cancer.
Right.
Yeah.
Very cool.
Yeah, so at the moment, people are exploring these kind of what they call personalized vaccines. So if you get cancer, you take a sample of the cancer, you sequence it, and then you make a personalized vaccine and
Right.
put it, and these work very well. The problem is it takes 8 to 12 weeks. It's expensive and it takes 8 to 12 weeks. With our method, we can literally make it within 1 to 2 days.
Yeah.
It's
So-
not, again,
Save
it's,
lives.
Yeah, so
it's a massive difference.
so-
Yeah, that's one in media.
Okay,
Yeah.
now I really get it.
Yeah.
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 Now I'll give you one more example. Like, so the other thing we're doing, so you're interested in the world's sustainability, right?
Yeah.
So basically 10% of the world's energy is used to archive digital information. So you have thousands of photographs on your phone, millions of emails on your computer, which you will never look at again.
Right.
We all know that, right?
Yeah.
But you'll never get rid of them,
No.
just in case, right?
Just in case.
Now, so all of that information all over the world is using energy, right?
Mhm.
Now we can store all that information in DNA
Mhm.
with no energy expended.
Yeah, we can do that. We can write that into the genomes of living things.
Yeah. So let me give you another
But how do
example.
you extract the
Oh,
data?
then
that's another-
You can sequence it,
Yeah.
right? And you are absolutely right. To
Okay.
have the full stack, you need 3 steps. You need the encoding of the information to
Mhm.
convert the 0 and 1s to
Right.
the GATC in the DNA
Computer
sequence.
stuff in the
right.
DNA.
So that we have a collaborator Shuki from Caltech,
Mhm.
right?
He
And,
helped the IBM build a parallel computer.
and then you need someone like me and Adrian to write the GATC into the genomes of living things, right? We do that. We have the writing,
Mhm.
and then as you said, how do you read it out, right? You need a like stack of reading, and for that we collaborate with Professor Hagen Bailey in Oxford.
Yeah.
Cool.
So another example, again, the sustainability angle, because that's really important to our civilizational level problems and sustainability. So another one is the increasing world population, right? So there was, as you know, a green revolution where our ability to produce crops more efficiently dramatically increased, but then just leveled off, right? So if there isn't a second green revolution to sustain the world's new population in 2060, we're going to have to mow down every remaining wilderness, rainforest, right? We're working on a synthetic chromosome called a neochromosome with some guys in Cambridge, and we can write many, many versions of these, which will help increase the yield of crops, make them drought resistant, heat resistant, pest resistant, so on and so forth. So it's another example of a kind of civilization level project that we're working on with huge implications for sustainability.
How are
And
you guys doing all these different things?
We figured out.
We figured out how to do it with collaboration. These are just two examples.
Yeah.
Another example is AI, right? So at the moment, AI can produce lots and lots of designs of proteins, for example, to make drugs, protein therapeutics, but they can't build them to test them. Right? So there's a huge discrepancy between our ability to design DNA and our ability to test it, make physical examples in the real world. And Kaihang's latest invention, which was published on Monday, shows that we can make DNA in a massively parallel manner, incredibly quickly, at a very low cost, efficiently, accurately, which can test all of these designs.
Cool. What do you think we might find in these? These are potential.
Oh, yes. What we may find in these AI designs.
Yeah, these AI
wonders.
Wonders,
yeah. So conceptually, I mean, if you think about it, the mathematical possibility of the DNA coding space is literally infinite, right? The possible proteins that can code is more than the atoms in the observed universe, right?
Yeah.
It's just like without that ability of the AI, we don't have a way to navigate in the infinity of that space.
Right.
Yeah.
But this is our first attempt to build like a portal that can allow us to realize into any spot in that infinity.
I actually see it as a time machine which travels outside time across this mathematical space of all possible biology, and then can just kind of materialize like the TARDIS. I don't know if you ever saw Doctor Who.
Can we create new animals?
Oh yeah,
with ethical concerns.
Yeah.
But
Right. I want a unicorn with wings.
Oh, well, that's
the question is, hang on, is this an order?
Yes.
We'll
I would like a pink
produce the
and purple
invoice.
unicorn with wings.
So the answer to that is that in order to map out the space of possible organisms, we need to be able to simulate them and compute them.
Right.
And to do that, we need to understand the generative laws of biology, which we don't yet understand, but we will.
I think
we have tested them.
I want to say that is exactly what Adrian's book is about.
Yes.
Okay,
The
great.
concept of the general biological intelligence.
That's right. Yeah, that is exactly
General
right.
biological
I call it artificial
I-
biological intelligence. What I mean by artificial biological intelligence is exactly that. So you say to me, hey, Adrian, build me a unicorn with, whatever features you want. And I say, yeah, okay, here's the genome that computes that creature that you've imagined, and not just its morphology, but its behavior, its anatomy, its physiology, right? Its biochemistry, right? Or I say, actually, sorry, but it's not computable. In other words, it's not possible, right? There's no developmental pathway that can take you there. Or maybe you say, hey, Adrian, make me a butterfly with wings the size of 5 tennis courts, or a human the size of a kind of flea, right? And I'll say, well, actually, human biology won't work at that scale because of surface tension, or a butterfly with wings the size of 4 tennis courts couldn't fly unless you put it up. But more kind of practically speaking, what you've got to realize is that evolution has only explored and tested the most infinitesimal fraction of all possibility, right? So imagine if you were to rewind the tape of life 1 million times and press the button again, you may never end up with a lettuce or a tomato or rice or maize. So there are all these useful species out there which we've never discovered. By turning a wild weed, tisonite, into maize, It enabled, mass agriculture, efficient agriculture, which enabled cities, which enabled culture,
Yeah.
which eventually led to gene editing, and then eventually led to our technologies, right? Genome writing, when suddenly culture feeds back into genetics, and suddenly you don't have to inherit the 4 billion years of evolutionary design. You can just take a blank slate and redesign from first principles.
With this, right, we can really have the freedom to design and
What's
construct,
possible.
right, and beyond just the single path that earthly life has endured, right?
Yeah.
And as I've been saying, right, it's like with this technology, we can realize things from the past, we can bring things from the future, we can even unwind the tape to ask the question, what if? Have a parallel universe.
And then run
right,
again.
Life's
Yeah.
gonna be like
Now,
that.
one of our co-founders, who sadly isn't here today, Brian He, has actually designed and built the first ever totally computer-generated biological entity. I say biological entity because it's a virus, which isn't technically living, because it has to infect a bacterium, right? But the sequence that the computer generated using a genome foundation model that he invented called EVO2 basically met the criterion for a new species because it had only 93% identity to the parental sequence. So technically, he wrote, designed, and built the first ever new species, right? But that's not a zebra, and it's not a hippopotamus, and it's not. But it's the beginning. And I've called this elsewhere the Wright Brothers moment of biology, when the plane goes into the air and bumps down after 90 seconds. But in that moment, when the Wright brothers took off, and you could anticipate the future of aviation, the Boeing 747, space travel, right?
It's the first baby step.
It's the beginning. It's like a baby babbling. We haven't learned how to speak the language fluently of biology, but we're beginning to speak it, in a very primitive way, right?
On that analogy.
Thank you.
I'm actually interviewing Samuel from Stanford.
He's great. Samuel works with Brian, who's our co-founder. He's in his
You
group.
were saying he had one of those big moments.
Yeah, he was involved in that work.
Okay.
Yeah. And actually, he never got. They never got the credit they deserved for that, because the public just didn't understand what they'd done, the significance. Like I said in my thing, that should have been front page New York Times. Those guys are pioneers.
So Samuel is the lead author on the synthetic phage paper. So phage is the virus against the bacteria.
Hey, if you're watching in 21,
they use the
26,
phage because it's very safe to us.
Okay, great. Well, thank you both so much.
Oh, pleasure.
I love how much enthusiasm and optimism you both have, and I'll be waiting for my custom unicorn with wings.
You have Adrian's word. Right?
Yes, you have it right. Yeah. We're taking that as an order, so we're going to invoice you for the go. But one last word, right, is that it's really important. First of all, and it's the key message of my book as well, by the way, that we're doing all of this synthetic biology, but we must value nature as a precious gift, if you like, that we're custodians of. We have no right to destroy nature. And as I said, you can see how synthetic biology can help us to preserve wilderness, rainforest, species. That's our primary aim, right? And we think we can help to do that by making everything biological. And the other thing is that this technology must be used safely, wisely, responsibly, ethically, in a morally reasonable manner, and in a manner that benefits society. So it's really important that we put that on record, and that's a key part of our company philosophy.
That's very important.
Yeah.
Well, thank you both for sharing your passion for what you do with me and my audience of bio enthusiasts. Thank you for answering all my questions. I feel like I have a much deeper understanding of what you're doing, and I'm excited to see the future.
Thank you so much for having us on the show.
Don't forget to subscribe or follow Talk Bio to Me on Spotify, Apple Podcasts, YouTube today for episodes dropping very soon.